All right, so now we're going to start talking about systems of equations, linear equations in three variables. So basically three equations with three unknowns. And so now we're going to use the same techniques, but we're going to expand it, what we've been doing, to three equations and three unknowns versus what we were doing before with two equations with two unknowns. Okay, so we're also going to talk about the idea of how many solutions we might have. We're also going to be looking at, like, instead of ordered pairs, now we're going to be looking at ordered triples. Okay, so let's jump right in with an example. Okay, so in this example, we're given a system of equations. Okay, and here they are. Okay, and so now we're given these ordered triples to test, just like we did at the beginning of when we were talking about systems of two equations and two variables. And so the same rule applies here as it did there. In order to be a solution for each of these ordered triples, in order for either one of these to be a solution to this system, we must plug in the values into each and every equation, and we must get a true statement for each and every system, or each and every equation. So that means when we plug this ordered triple into this equation, we should get a true statement, -2 equal to -2. And if we plug that same point into this equation, we should get 24 equals 24. And into the third equation, we should get 0 equals 0. If we don't, if we get something like 2 equals 3 or something like -3 equals 0, then that is a false statement, and therefore this system has, or excuse me, this ordered triple would not be a solution to the system. So as soon as we get an answer that is not true, then we're done, right? So if it happens with the first one, we don't have to go ahead and check the other two, because if we get a contradiction here, then it doesn't matter if the other two are true statements. Okay, so let's do that. So the first thing we're going to do is we're going to just plug the values in, right? So we're going to plug in 3 for x. So here, 3 for x. -5 for y, and 1 for z. Okay, and so if we do that, we get what? We get 2 times 3 minus -5 minus 3 times 1, right? And so we just evaluate it, right? And so we get 6 plus 5 minus 3. And so this will give me what? This is going to give me 11 minus 3, which is 8, right? So now double check to make sure we didn't make a mistake. So x, y, and z, and let me make sure I didn't write this down incorrectly. Oh, I'm sorry, I did. This should be a plus, which means that's a plus. Let me make sure, because it looked like a subtraction. So minus 3z, x minus 4y plus z, and -3 minus y plus 4z. Okay, so now let's redo this. So this would be minus, right? So that would be minus. And so what do we get? So we get 6 minus 5, which is 1, and then minus 3 equals -2, right? So this will give us 1 minus 3, and that'll give us -2, which is equal to -2. So we get a true statement here. Okay, now let's do it again for the second equation. So now we're going to plug in 3, so it's going to be 3 minus 4 times negative 5 plus 1, right? Okay, so now if we obviously we want to do this first, so it'll be 3, and then this is going to be plus, right? Plus 20 plus 1, which adds up to 24. So we get 24 equals 24. All right, so far so good. So now we have to go on to the third one, and if it works for the third one, then we've got a solution. If it doesn't, then we don't. So now we're going to do negative 3 times 3 minus a negative 5 plus 4 times 1, and we should get 0, right? Okay, so now this will give us negative 9, this will give us plus 5, and then this will give us plus 4, and of course we get negative 9 plus 9, which equals 0. And we're done. So now, what we've just shown is we proved that this ordered triple is a solution to this system. Okay? Now, let's try with the part B with the other ordered triple. So we're going to do the same thing. So we'll plug these values into the first equation and see what happens, and then we'll start going to each one. So now we're going to plug 2 into x, right? So that'll give us 2 times 2 plus y, which is negative 3, and then minus 3 times z, which is 1. Okay? So now let's start off and say, okay, we got 4, we get minus 3, right? And so what do we get? We get 4 minus 6, which equals negative 2. So far, so good. So we get negative 2 equals negative 2. Okay, now we're going to go to the second equation. And with the second equation, again, we're going to plug in 2, negative 3, and 1. So it's going to be 2 minus 4 times y, which is negative 3, plus z, which is 1. Okay, now let's see if we get 24. Okay, so far I don't think it's going to work. So we get 2 plus 12 plus 1, which is going to equal 15. So it didn't work. Okay, now double check, make sure I didn't make another mistake. So 2, and then minus 4 times negative 3, plus z, which is 1. So yeah, so this gives us positive 12, and then 12 plus 3 is 15. So 15 does not equal 24, so we're done. We don't even need to check the third equation, we're done. So what we've shown is that this ordered pair is not a solution to the system of equations, and we're done. See you next time.